dipole antenna. Okay, here when we are discussing about this half wave dipole antenna or any antenna, the procedure is same. What is the procedure? First of all, we will calculate the vector potential. From the vector potential, we will calculate the magnetic field intensity. From the magnetic field intensity, we will compute the electric field intensity. If you know the magnetic field intensity and the electric field intensity, we can easily calculate the average power. What is the average power? The half of the magnitude of electric field component multiplied by the magnetic field component will get the average power. If you integrate the average power over the surface area of the sphere ds, you will get the total power. Okay, if you know the total power and the average power, we can calculate the radiation resistance we can calculate, and also directivity also we can able to calculate. Okay, that is the same procedure for all antennas. Okay, in this antennas and wave propagation first unit, we have three derivations are there. One is for sharp dipole antenna, other one is for half wave dipole antenna or quarter wave monopole antenna, another one is loop antenna. These three derivations are there. They are important. If you can able to remember these equations, you'll score good marks. Okay, full marks. Okay, in the examination also. Okay, let me start here. The half wave dipole antenna. Here it is a dipole, means it has two poles. This is one pole and this is another pole. Okay. In other words, this dipole antenna is a symmetric antenna. How can you say that is a symmetric antenna? Okay, if I am placing this half wave dipole antenna in a z axis, let us say this is positive z axis and this is negative z axis, and this line in between this line, this is the z is equal to 0 line. Okay, this dipole antenna is symmetric about this z is equal to 0 line. Okay, now last class we have seen that if you are considering a small portion of this antenna conducting material, okay, let us say the size of this is dz, the length of this portion, okay, what I am highlighted here is a little amount of this area. Okay, the length is dz. If the current is passing through this element is I, okay, the total current passing through this component is this is I into dz. Okay, initially we'll compute the vector potential at a distant point r. Okay, uh, r due to this I into dz, due to this small current element. Okay, after that we will integrate from entire minus h to plus h. We'll get the vector potential. Okay, the complete vector potential we will calculate. Okay, here the current in the half wave dipole antenna, the current distribution in the half wave dipole antenna is a sinusoidal. That's why we are assuming here is equal to Im. Im is the maximum current in this direction. Im sin beta h minus z. What is this beta? Beta is the phase shift constant. Okay, 2 pi by lambda. H is the length of this antenna. This is the h. H is equal to L by 2. Here, the length of this antenna in half wave dipole antenna, the length of the antenna is lambda by 2. This is a half wave. What is the half wave? Half, that meaning is half wavelength. Half wavelength. Okay. Therefore, the length of this dipole is h is equal to L by 2. What is L? L is equal to lambda by 2. Lambda by 2 by 2. This is lambda by 4 and this is another lambda by 4. Okay, you have to keep in your mind. The radiation pattern of half wave dipole antenna and quarter wave monopole antenna are similar. Why? Because see, if you take only the half portion of this antenna, it is looking like it is a monopole antenna. If you take half at the z is equal to 0 axis, if you take this antenna, this is also looking like the half wave dipole antenna only. Okay, and what is the length of this quarter wave monopole? Mono means single pole. Single pole means it has got only one pole. Okay, what is the length here? This is a quarter wave monopole. The length is equal to the length of this antenna is equal h is equal to L by 2. Here this is also lambda by 4. That's why the radiation pattern of half wave dipole antenna and quarter wave monopole antenna are similar. Why? Because it has the same. Here, same thing is repeated here. Okay, But quarter wave monopole antenna we are considering up to here only. We are connecting the remaining portion to the perfect ground. Okay, that's why the derivation part, everything is similar for the quarter wave monopole antenna also. The main difference is the radiation resistance of the half wave dipole antenna. If it is R, the radiation resistance of the quarter wave monopole antenna is capital R by 2. Okay, that is the only difference we'll prove in short time. Okay, here the waves, so see here, suppose let us assuming we are a current element is here, there is another current element is here. Okay, here we can see that suppose there is an observation point, let us say we are having an observation point here. The wave that is coming from this point, okay, has to travel little more distance compared to the wave front that is coming from this current element. Okay, here the difference is called the path difference. Okay, this path difference, if you calculate, okay, this is theta, this is also theta. Okay, this path difference is z cos theta. Okay, that's why this is the reference point. Actually, this is the reference point from where we are measuring the vector potential. Okay, what is the path difference here? This is the R, and this is also capital R. This small amount is this distance is called the z cos theta. That is the path difference. You have to keep in mind that in R we can write R is equal to, this is the total distance capital R minus z cos theta. Z cos theta is the path difference. Okay, you have to remember that point also. Now we have seen these things. The length of the half wave dipole antenna is equal to L is equal to 2h. This is lambda by 2. Okay, similar the figures is there. For the current distribution in the positive z axis, okay, the positive z axis we are assuming the current distribution is Im sin beta h minus z, and the negative z direction Im sin beta h plus z. Okay, that's here written here. Now the current element I of z, okay, due to the I of z, we have to calculate the differential, okay, vector potential at a point P. At a point P, we'll find out the first. After that, we'll integrate with respect to minus h to plus h. We'll get the total vector potential. Okay, this formula you have to remember. The vector potential, the differential vector potential equal to mu by 4 pi r. What is the r? Capital R is the distance where we are measuring the observation point to that current element. Okay, this is the capital R. Okay, this is equal to e power minus j beta r. What is the beta? Beta is the phase shift constant. Phase shift constant is equal to 2 pi by lambda. Okay, now this is the differential potential, vector potential at a point P. Now, due to the current element IDZ, this is a small current element here. This is the small current element. Now we have to calculate the total vector potential due to this entire dipole antenna. That is, okay, how we will get? That is, we can integrate from minus h to plus h with respect to dz. We will get the total vector potential. Okay. From here onwards, it's very simple. If you arrive at this point, here from here onwards, we'll substitute the simply substituting and simplifying the equations will solve this vector potential. Once vector potential is known, we'll compute the magnetic field intensity and electric field intensity. Here, one more important point is you have to remember that here the waveform is traveling in. Okay, let us say this is an observation point here. Okay, if you see that the electromagnetic wave is traveling in this direction, R direction. Okay, and also we can see that, the due to this vector potential capital A, the vector potential capital A, okay, that capital A is also in the z direction. Okay, the capital A is in z direction. Okay, due to that AZ, it has a magnetic field in the phi direction. Okay, you have to remember this magnetic field in the phi direction, and the electric field is in the theta direction. You have to remember these things. Okay, this is R direction. Okay, the wave is traveling in R direction. The electromagnetic waves are traveling in R direction. Okay, the magnetic electromagnetic fields they are perpendicular to the direction of propagation, and also they are mutually perpendicular. Okay, here we are having the magnetic field component is having magnetic field is having phi component, and the electric field is having theta component. You have to understand these things. You have to keep in your mind. R is the R unit vector R. This is the direction of the R. Okay, the wave is propagating in this direction. Okay, the wave has a electric field and magnetic field. Magnetic field has phi component and electric field has having theta component. For this half wave dipole antenna, you have to remember these things. Okay, therefore, now we have computed the total vector potential A. Okay, from that we'll compute the total vector potential. We have to simplify this one first of all. Okay, this is minus h to plus h. Now we can split the integration from minus h to 0 and 0 to h. Okay, simply you can write like this: minus h to 0 and 0 to h. Same equation. Just I'm writing this equation. Now substitute the current distribution in minus h to 0. This is Im sin beta h plus z. Similarly, for the positive z direction, 0 to h positive z direction, this is Im sin beta h minus z. Okay, here for our mathematical simplification, here we are assuming that here capital R we are writing with respect to small r. Why we want to write it with respect to small r? Because in spherical coordinate system, we are taking the reference point. Based on the reference point, we will compute the vector potential. That's why we are using this R is equal to Z. R is equal to capital R minus Z cos theta. This is the reference point in spherical coordinate system. Okay. Here what we have to the assumptions is in numerator will replace the capital R is equal to R minus Z cos theta, but denominator for simplification purpose here we are assuming capital R is equal to small r, because in far fields, okay, in far fields the distance from the if the distance from the antenna is very far, okay, this path difference is negligible. Okay, that's why, okay, in denominator we are assuming the capital R is equal to small r. Okay, this is only assumption. Okay, remaining all are very we are just substituting the values in this equation. Okay, now now this above equation will become after substitution of capital R is equal to small r in the denominator, and numerator capital R is equal to, where is the capital R? Here capital R is equal to R minus Z cos theta. We will get this expression. Now here we have to integrate with respect to dz. Therefore, we'll keep all the dz terms. Okay, we are keeping all the dz terms, z terms inside, and we'll bring out all the other terms outside. Now, see, this is Im sin beta h minus z plus e power minus j beta r dz plus 0. Same thing here. I have written here, same thing. Okay, here e power minus j beta r, I'm writing e power minus j beta r into e power minus or minus plus j beta z into cos theta. Okay, now I'm bringing out, because it doesn't have any z component, that's why I'm writing here. Now, this sin beta h into z, this can be written as sin beta h plus beta z. Okay, we already know that this beta h, sin beta h is nothing but, what is this? Beta is equal to 2 pi by lambda. What is the h? H is the length of the half wave dipole antenna. Okay, what is the h? What is the h? H value? Can anybody tell me what is the h value? In half wave dipole antenna, the length of the antenna is equal to L is equal to lambda by 2, but h is equal to L by 2. Therefore, h is equal to, in terms of lambda, that is lambda by 4. Bh is equal to 5 by 2 will get. Okay. Now we have to substitute Bh is equal to 5 by 2 in this equation. cos pi by 2 plus theta, sin pi by 2 plus theta equal to cos theta. That's why you are writing, we are getting this one. Now replace sin b beta times of h plus z in this, replace this with cos beta z, will get this equation here. Now here I am doing little bit adjustment to make the upper limit and lower limit similar. Here replacing z with minus z. If you replace z with minus z, we can interchange this, these limits. Okay, cos of minus z is equal to cos z only. That's e power of minus z, z plus we have replaced with minus z, e power minus j beta z into cos theta and dz. Okay, now here the upper limits and lower limit are both are similar. Now we can write this thing in a single integration. Okay, see here, cos beta z is common here. You can write like this. This is looking like e power j theta minus e power j theta plus e power minus j theta. This is nothing but 2 times of cos theta. You can write cos theta is theta is dz cos theta. That's why you can write like this. This is looking like cos 2 cos the 2 cos a cos b, 2 cos a, 2 times of cos a cos b. Let us say this is a, this is b. What is the 2 cos a cos b? That is equal to cos a plus b plus cos a minus b. Okay, in this time you can write like this. We are getting cos a plus b plus cos of a minus b. Therefore, if you bring out this b of bz term, this is writing as, you can write as cos of bz 1 plus cos theta plus cos of bz 1 minus cos theta. Now we can do the integration. What is integration of cos? Integration of cos equal to sin theta. And again here theta also it is having some value, right? We have to differentiate with respect to z and we have to divide that with that value. How, what you are getting here, the integration of cos is equal to sin bz 1 plus cos theta, and we have to, again we have to differentiate in inside term bz into 1 plus cos theta, that is beta times of 1 plus cos theta will get like this. Okay, similarly here also we are getting this term. B is constant, that's why we are bringing outside. B is common here, that's why I'm bringing outside here. Now take the LCM, a plus b a minus b square minus b square. Therefore this we will multiply this 1 minus cos theta with this term and 1 plus cos theta with this term. We are getting like this. Okay, now substitute BH, we already computed. BH is equal to pi by 2. Here, this 1 minus cos theta I am writing here. This is sin pi by 2 1 plus cos theta. If you take pi by 2 inside this brackets, okay, here we are getting, see what we are getting here, sin pi by 2 plus cos theta. Sin pi by 2 plus pi by 2 cos theta we are getting. Sin pi by 2 theta is equal to cos theta only. That's why I am writing cos pi by 2 cos theta. Here also, this is also cos pi by 2 cos theta. Okay, if you multiply these terms here, cos pi by 2 cos theta minus of cos theta and cos pi by 2 cos theta. Here minus will come, here plus will come, that both will get cancelled. We are getting cos pi by 2 cos theta here and another cos pi by 2 cos theta here. That is equal to 2 cos pi by 2 cos theta. We are getting divided by sin square theta. Okay, simplification, just a simplification we are getting. This is the final expression for the vector potential. Okay, here we are doing only the simplification, we are finding out the vector potential here. Okay, now you know the vector potential. From vector potential we can able to compute the magnetic field intensity. How it will computed? Normally we know that the magnetic flux density is equal to del cross A. Okay, here the magnetic field is having only pi component. In our last class also we have seen the current is in z direction, it has only AZ component. From AZ component we will see that it has a magnetic field has got only phi component. Okay, same thing is using here. That's why here I am computing the phi component only, remaining terms are 0. How to compute the phi component? This is the curl of the vector potential. You have to remember, all of you have to remember, for curl of any function, this is the same in spherical coordinate system. Okay, you have to remember this. Okay, now, okay, how will get the phi component? This is the phi component, right? Okay, how to compute the phi component? 1 by r square sin theta. Phi component is multiplied by r sin theta, right? This r sin theta into, you have to eliminate this row and this column. Now, dou by dou r of ar theta minus dou by dou theta of ar. Okay, see here, we are getting this expression. Okay, here you have to know that, okay, the electromagnetic waves traveling in the r direction. In this case, electromagnetic field has h phi and e theta component. It doesn't have any r component. Therefore, the wave is not having any component in this r direction. Therefore, this term is equal to 0. Keep this term equal to 0. Now, this equation you can write as 1 by r square sin theta, r sin theta into dou by dou r of r a theta. You can cancel this r sin theta term and r square sin theta term here. We are getting 1 by r dou by dou r of r times of a theta. A theta in spherical coordinate system, you can write it as a theta is equal to minus az sin theta. Substitute here and also substitute az value. What is az? This az value in this equation. Okay. Here del cross a bar is equal to mu times of h phi. Substitute here in this equation. Is equal to mu times of h phi is equal to 1 by r dou by dou r of 1 by r dou by dou r of r times of minus az into sin theta, r times of dou by dou r. This is the r you have written here, I think, minus az into sin theta. What is the az? This is the az into sin theta. Okay, this is minus r az into sin theta. Here you have to differentiate with respect to r. Keep all the r terms inside and bring out remaining all terms. Okay, you are getting dou by dou r of e power minus j beta r. Okay, if you, what is the differentiation of e power j theta? E power j theta only. And if you differentiate the minus j beta r with respect to r, it will be getting minus j beta. R is 1. Okay, differentiation of r is 1. Therefore, we are getting, this is the expression. Okay, in 10 minutes this meeting will close. I will take the attendance first and then we'll continue. This is the h phi value. Okay, further you can say that mu times of h phi is equal to this value. If you come this cancel this mu term here and this mu term here, we are getting the h phi. H phi is, this is the equation. If you take the magnitude of h phi, you are getting this one. The units for this is amplitude, is amperes per meter square. This is the expression for the magnetic field intensity. Similarly, for electric field intensity also, you can compute very easily. The relationship between electric field intensity and magnetic field intensity, E theta by h phi is equal to eta naught. Okay, therefore eta naught equal to, therefore E theta equal to eta naught into h phi. Okay, this is a simple way we can compute the electric field component. Is equal to eta naught into h phi. H phi value already computed, right? This is the h phi value. We compute here, we'll get E theta is equal to j times of, this is eta naught equal to 120 pi. Substitute 120 pi here, 120 pi j into 120 pi into im by 2 pi r e power minus j beta r. This term is similar. Now cancel this one 2 times and 60 times. J times of 60 im by r. This 2 pi and this pi will get cancelled. E power minus j beta r cos pi by 2 cos theta sin theta. The units for this electric field intensity is volts per meter. Magnetic field intensity is amperes per meter square. Okay, that is the thing you have to remember. Okay, I will take attendance at here. Okay, here what you have done is you have computed the vector potential. From vector potential, you computed the magnetic field component h phi. From h phi, you are computing the electric field component E theta. If you know the magnetic field component and electric field component, you can able to compute the average power. From average power, you can compute the total power. From total power equation, you get the radiation resistance. And also you can able to compute the directivity also. Okay, we'll discuss later. Now, can somebody help me to take the attendance, please? Who is going to help me? Yes. Anybody is having good connection? Internet connection,
Yes,
please help.
sir.
Swarup is there. Very good. He will help. He will help me. Swarup, please tell me.
Sir.
Yes.
88, 92.
83 వచ్చారా?
No, sir.
86. 86.
88,
88.
92, 93.
92. చాలా తక్కువ క్లాస్ వచ్చినట్టు. 92, 93.
94, 96.
94, 96.
97, 98.
97. 97, 98.
99, A0, A1, A2, A3.
99, A0, A1, A2, A3.
A4, A5, A6, A7.
A4, A5, A6, A7.
B0, B1, B2, B3, B4.
B0, B1, B2, B3, B4.
B5, B6, B8.
B5, B6, B8.
B9, C0, C1, C2, C3, C4.
C1, C2,
B9,
C3. C4.
C5, C6.
C5, C6.
C9,
C5, C6 తర్వాత
C9, sir.
C6 తర్వాత C9. ఓకే.
D1, D4.
D1, D4.
D5, D6, D7.
D5, D6, D7.
D9, E1.
9, E1.
E3, E4.
E3, E4. E2 వచ్చారా?
Yes, sir.
E2 రాలా?
No, sir. No, sir.
E3, E4.
E6.
E6.
F0, F1.
F0. F1.
F3, F4.
F3, F4.
F5, F6, F7. F5 రాలేదు.
F6, F7.
F7. G2.
G2.
F9.
F9.
A9, sir.
F9, A9.
లాస్ట్ లో ఉన్నాడు A9.
A9 అంటే ఓకే. A9 వచ్చి రాకేష్ కదా, రాకేష్ మోహన్. ఓకే అమ్మా. నేను
ఎవరన్నా నెంబర్ చెప్పలేదేమో కనుక్కోండి సార్ ఒకసారి.
నేను ఆప్షన్ లిస్ట్ చెప్తున్నాను. F7
చెప్పాను.
F7 వేసాను. నేను ఆప్షన్ లిస్ట్ చదువుతాను, ఒకసారి చూడండి. ఆప్షన్ లిస్ట్ చూస్తాను. 83, 84, 87, 89, 90, 91, 92, 93, 95. 95 తర్వాత
92 వచ్చాను సార్.
92 వచ్చావా? ఓకే. 92 వేసా. నెక్స్ట్ అమ్మా A4 కాదు, A8, B7 తర్వాత C7, C8, D0, D2, E2, E5 తర్వాత E7, E8, E9, F2, F5, F8, G1. వీళ్ళు ఆప్షన్.
సార్ G1 వచ్చాడు.
G1 వచ్చారా? E1.
అంతే
Okay, thank you, Swarup. Okay, here we will complete this one. Okay. Now we can compute the radiation resistance of half-wave dipole antenna. How to compute the radiation resistance? Okay, that will be computed by calculating the total radiated power. Total radiated power is equal to, this is the expression, right? Integration with respect to theta and pi, P average into ds. Okay, ds is equal to, we already know, r d theta, r sin theta d phi. This also equal to, okay, here only pi term is there, no? The pi varies from 0 to 2 pi. If you integrate with respect to d pi, you will get 2 pi times of r into r square sin theta d theta. Okay, ds you can write as ds equal to 2 pi r square sin theta d pi. Don't confuse here. I am not doing with respect to integration with respect to phi. Why? Because anyhow doing replacing 0 to phi is nothing but 2 pi minus 0, that is equal to 2 pi. That's why I'm writing here in short form. Now we will integrate P average with respect to ds, the ds value here. Okay, now P average is equal to half times of E theta H phi. Okay, simply substitute here and we'll get square terms. All are square times, 1 by 2 times of the square terms we will get. This is the average power. Okay, from the average power we'll compute the total radiated power. Total radiated power means the pi value, sorry, theta value, it varies from 0 to pi. This is the, what is this? This is the P average into ds. ds equal to 2 pi r square sin theta d theta. Okay, again I'm telling d phi is there. I am not substituting here d pi. Simply with respect to d pi, we are writing 2 pi. Okay, that's why here we are doing the only single integration. Otherwise, we have multiple double integration with respect to theta and pi is there. Okay, now the sine square term, sine term and sine square term is there. This will cancel. This pi r square and pi r square term will get cancelled. Now we are having 15 to the 30 im square. Now here we are integrating with respect to theta. Keep all the theta terms inside and remaining all the terms outside.